Robot software is like the brain of the robot. Good and efficient software can even turn the crappy hardware into a good outcome, and the same holds true vice versa. Here, we will share the tools and techniques we have used to build our robot. We have considered this competition more as a chance to explore new possibilities of effective coding rather than competing among the teams. Sometimes trying everything mentioned here in this video might not be possible if you are new to programming, but the idea of sharing is to raise awareness of these things. You might have got into a situation where team members have to get together and code at once. But what is traditionally done is that members code the same program in different computers with different copies and try to upload their copies to the robot and check. There are many collaborative coding tools on the internet such as codeshare.io, REPL.it, and Microsoft LiveShare extension for VS Code. With the use of these tools, our members were able to code the same program at the same time and watch edits from other members live. We have used VS Code to code the robot software and REPL.it for the simulation for the algorithm of the maze. Many of you watching the video might have experienced this scenario for sure, where you have saved many versions of your beloved code to make sure a mistaken dot or comma won't ruin your code when the compiler just doesn't find the error. Here's how we have done this in one of our previous competitions back in 2018. That's when version control systems come in handy to give an effective and easy solution. There are many version control tools such as Git and Mercury, but here we have used Git for our project. Git is a simple command line interface where we can commit, add branches, merge commits, and many more. To give access to our Git repository to all our members, it should be stored in a common location. We can even simply add them to OneDrive or Google Drive, but there are famous platforms built for this. Some popular common platforms builds are GitHub, Bitbucket, and GitLab. Here we have used GitHub to host our Git repository. Many of you might think that we have used Arduino to develop our robot, as most of the robotic teams are. Arduino has changed the world by enabling the robotics industry to anyone. Arduino is a great platform to develop products without prior knowledge, but it comes with many downfalls. Many of the Arduino boards that we use currently are based on AVR architecture and are less powerful. ARM-based industrial boards are used to make professional products, and in the past it has been really hard to learn programming these industrial boards. Most of the content is not available on the internet those days. We wanted to change from Arduino and to learn to use industrial boards, and we were the first undergraduate robotics team to try and be successful in that. The ARM community has been developing, and we think now it has come to a position where many content is available on the internet. Here is a very simple comparison between the microcontroller board that we have used called STM Nucleo F4 series versus the traditional Arduino Uno board. As you can see, STM has a higher bit rate, enabling faster calculation speed by using fewer clock cycles per arithmetic. It also possesses much faster clock speed by using phase lock loop. and also it has much higher flash memory and SRAM, more interrupt pins and etc. By every means, it can be seen that STM boards are powerful and it's even cheaper than the original version of Arduino boards. But the problem is the steep learning curve of using these industrial boards. It's good to learn STM before going to the industry. There are many common tools used to program STM boards such as the well-known STM Cube Programmer, Keel, Embed Studio, and etc. Here, we won't dive deep into this topic as it's a very wide area. We have tried to code in a modular way where we have functions to every small task and we use other smaller functions to make larger functions. It has increased the understandability of the code and for members to work on different coding levels at the same time. We had a method to save many codes in our robot for testing many functions without being able to upload the code again. To achieve this, we have used a button panel to move through the settings and the functions. We have also used object-oriented programming techniques to reduce code duplication. Some examples are the color sensor object and the encoder object. In the color sensor object, we have included some of the functions like read color, calibrate mode, and read calibrated color. And for the encoder object, we have used functions like encoder count, travel distance, and traveling speed. One of the major difficulties we have faced with using STM is we were unable to find the libraries written for some sensors like the display module, color sensor, and the line follow sensor of our robot, which we had to write libraries on our own. But it was a wonderful experience and a challenge we had to overcome. We had to allocate a considerable amount of time to overcome these challenges.
While building the physical robot, we could parallelly develop the algorithm which needed to complete the task using this record.it online compile. Here we can share the project and work online with the team members. The specialty of the way we developed this algorithm was we created our own method of visualizing the grid with the position of the robot. This simulation process was hugely helpful us to find and fix bugs of the code without wasting our time. Here, as you can see, we categorize different functions of the code as implementation, logic, position, definitions, etc. and imported all required .h files to the main code and developed the task flow in this main file. First, we have given this test grid as an input to check whether we would get the exact same grid after robot traversing the grid. We use numbers 0, 1, 2, 3 to represent colors white, red, green and blue respectively. We can change positions of the color squares in the test grid as we require. Here we can see the grid which has not yet been mapped when the robot is on the entering position of the grid. Robot is headed to the north direction as you can see here. Next, when we run this map maze function, robot travels through the grid and stop at the 6-2 position as robot has found all the 9 color squares in the grid by then. Here the robot is headed to the south direction as you can see. As we have planned to use the optimal method to map the grid, we didn't traverse along every row of the grid. We skipped half of the rows as mentioned before. So while traversing along a row, we had to calculate values of the squares in both sides of the robot. And here it shows the right and left cell coordinates with respect to the current position. This is the saved grid by robot after traversing along the grid. This is exactly same as the grid we have given. Then we calculate the values of the squares and you can see here all the calculated values. Next we have filtered out all the 9 color cells with coordinates and values. Then this is the order we should drop the color coins, and these are the selected 3 color squares out of all 9 color squares. Now we can run this drop coins function and see the positions of the robot at each time before and after dropping a coin. First we drop the blue coin. This is the position before dropping the coin, and this is the position after dropping the coin. Likewise, next we drop the red coin, and these are the relevant positions. Finally, we drop the green coin according to the calculated order. After dropping all coins, we exit the grid, and for that we can run go to ending node function. Then the robot's position can be seen like this at the lower right corner. It's worth mentioning that when the robot was dropping coins, we always planned the shortest path to navigate to the relevant position with respect to the current position.